paper is on Naval Survivability, Impact on Design and Construction. There are two speakers, Mr. Vivek Ramnath and Mr. Jose Paul. Mr. Vivek Ramnath is a graduate from QSAT. He's also done his master's from University of Newcastle upon Tyne as a part of his Commonwealth Fellowship program. He specializes or he manages a team of finite element analysis, CFD and acoustics, including electromagnetics for naval platforms. Mr. Jose Paul is a naval architect in Cochin Shipyard. So there is a paper where the design team and the shipyard have combined together to produce a paper. He has a dual degree in naval architecture from IIT Madras, that is what we call BTech and MTech, and he has been working in CSL in the basic design section. He has also worked for the passenger vessel, 1200 passenger vessel for the Andaman and Nicobar Islands, including the anti-submarine warfare, or what as we call it, ASW corvettes for the Indian Navy, the next generation corvettes. So I request both the speakers, I think both of you are presenting? Yeah. Request both of the speakers to come to the dais and request to keep the presentation within 20 minutes.
Good afternoon. Thank you, Chair Professor O.P. Shah, doyens of the industry, officers from the Indian Navy, my professors, friends, ladies and gentlemen. So today's presentation is about naval survivability and its impact on design and construction of warships. Myself, Vivek Ramnath, Deputy General Manager, SEDS, and along with me, Sir Jose Paul, Deputy Manager at Cochin Shipyard, will be presenting this. So the presentations before us were all about optimization, green shipping, green technology, green fuels. So we thought, why not a contrast? Because we have people from large defense companies, officers from the Navy, so we should do some justification. So we took a topic which is unfortunately not very green, but very interesting, which is about survivability of ships, of naval ships. And when we talk about survivability, the contents are survivability and its three components: susceptibility, vulnerability, and recoverability of ships. And then we have a concluding remarks and then references. So this is the motivation why we are here. The anti-submarine warfare shallow water corvettes, which are being built for the Indian Navy under construction at Cochin Shipyard, where SEDS and CSL are joining hands to design and to produce these ships. Unlike commercial vessels, where the interest or the point of optimization is to reduce fuel consumption, to maximize cargo carrying capacity, for a naval ship, the focus should be on surviving a combat mission. That's why two gentlemen, there are many definitions for survivability. I just put one by R.E. Ball and C.N. Calvano, is that the survivability is the capability of a ship to withstand a man-made hostile environment. Now, when we look at survivability, there are three basic components: susceptibility, which is basically avoidance of detection; vulnerability, which is your resilience under attack; and recoverability, which is survival post-attack. And when we look at susceptibility, the first one, it's not just, avoidance of detection means you reducing your signature in different domains, getting threat warnings in advance, using expendables and decoys, jamming and deceiving measures, as well as tactics and training. For vulnerability, you have to look at your residual strength, damage stability, your shock resistance in nuclear, biological and chemical defense, armor and shielding, giving appropriate redundancy for the components, compartment disposition, etc. And recoverability is about battle damage control and restoration of system capabilities. This is the same thing, but we have put it in order. That green one is the susceptibility part, where you try to avoid getting detected in the first place, and you try to detect the enemy before they detect you, and you respond to that threat. In case that is not possible, you try to prevent locking on of the enemy missiles or other threats using different techniques like electronic countermeasures or expendables, etc., like decoys. Vulnerability is about the selection, disposition, as well as integration of weapons. And how you destroy a threat, for example, close-in weapon systems or missile defense systems, and also resisting the threat effects. Like if you are attacked, how you design it and build it such that the threats are within certain limits. And then recoverability is about controlling the damage, and replacing, reconfiguring, and restoring the capability of the system. Susceptibility, as I mentioned, the first thing is about signatures. You have many different types of signatures which can be detected by your enemy. So you look at different aspects like your radar signature, your the high frequency communication which can be detected, tracked by your enemy, laser signature which can be used by the enemy for ranging, optical signature, hydrodynamic pressure which can be detected by multi-influence mines and get activated, magnetic signature, acoustic signature, very important for the ships that we are working on, the anti-submarine warfare vessels, underwater electric potential, wake, which torpedoes could be used to home in, infrared signature from heating of your hull as well as your exhaust plume. So there are multi types of signatures. Optical signature, now mostly only for the total combat operations where your vessel is operating against a background. For example, you see two different types of, two different vessels of the same class, USS Freedom class littoral combat ships, USS Freedom and USS Fort Worth, where they have used different camouflage paintings, designed for operation in different areas. You can see that they're kind of merging the background. Radar signature, very important. These are like, if the enemy has got these radars, they will be tracking you, trying to classify you. I've just put two pictures here. One is a Thales NS200 AESA S-band radar and a BAE Samson multifunction radar. A multifunction radar basically can be used for surveillance as well as fire control. Now, how will you control this? On the right you see is a Singapore Navy ship, RSS Formidable, and there could be many options like using radar absorbent materials, radar opaque materials, radar suppression materials, and radar transparent materials, in addition to shaping and usage of appropriate materials. So how you use it depends on your knowledge as well as your experience. And on the left, what you see is a radar cross-section polar plot, which is a high-frequency analysis using an appropriate electromagnetic tool. And what you see is how your ship will be seen in a radar, or how much reflectivity is there in a radar perspective. Jose, can you please?
Adding on to what Vivek has just said, I'll try to touch upon some of the areas of focus for the yard. First is the construction difficulties, especially with the shaping in the hull and the superstructure. Second would be the procurement, identification and procurement of special materials and special paints. Next would be identification and procurement of radar suppression screens and closures which are not readily available and mostly have to be custom made to suit the vessel. And lastly, we will have to pay a lot of attention to details of the exposed fittings which will contribute to RCS. Majority of the deck machinery are standard designs from OEMs, so we will have much less flexibility in those.
Thank you. Next, very important one for the anti-submarine operations is your acoustic signature. And there are multiple types of sonars available. I have just put two of them which are commonly seen on ships. Especially the hull-mounted sonars are there on many ships which will be using acoustic sensing. And the one on the left is a towed array sonar, or a towed active/passive variable depth sonar. There are different types of it. A submarine might be using a bow array and a flanking array which will be trying to track you. And how will you reduce your acoustic signature, or the signature which you transmit or radiate into the water? On the right bottom you see here is an approximate diagram, free body diagram of an equipment mounted resiliently to the hull structure through a seating. So the best option would be to silence the equipment, the noise source itself. So you'll have to give appropriate limits to the manufacturer, which are both practical as well as not very complacent. Then next you have to look at the resilient mounting system. You have to design it such that the dynamic stiffness, the dynamic ratios are not adding to the roll resonance of the equipment and its excitation frequencies. Like if you're going in an SUV and taking a curve, you will have that roll, body roll. Something similar to it should not happen, which will add to the attenuation. That's on the left bottom. What you see is that. And on top is an impedance analysis of the structural foundation, where impedance is the quality of the structure to attenuate the noise which is getting transmitted or which is passing through it. And on the right, what you see is an acoustic radiation analysis, which finally how the noise is radiated into the water. It's the fluid structure interaction one, and you can you can integrate the sound pressure levels and power levels and understand how much noise is getting radiated, and finally, is it within your limits. Next is the yard slide.
When it comes to URN of a vessel, yard's major point of concern comes to the procurement challenges, especially with that of the major equipment, which will have to meet specific noise values, both in terms of SBN and ABN. And also, you will have shelf life and storage requirements for the mounts and the rubber elements used to meet these targets. So you will have to be paying attention to those too. Also, additional quality control checkpoints has to be established when you compare it with the commercial vessels to make sure that the design aspects are accurately captured in the construction phase also.
Thank you. Next is infrared signature suppression. This is the data from W.R. Davis. This is not my data. But I'm just presenting it to show you how important it is to attenuate or suppress the infrared signature. On the bottom you see are the images through an infrared camera of the same ship using 4 different infrared suppression mechanisms. The first one has no suppression. The second one is an NBC manual wash, which means the hull is cooled with certain water through something called a pre-wetting system. And the third one is a full hull structure cooling using nozzles through water. And the last one is, the third one also has an exhaust cooling mechanism, a passive cooling mechanism called an ejector diffuser. And the last one is a full cooling. And what you see is the difference in time that a missile take, an anti-ship missile takes to lock onto your ship after your ship detects it. So you can see that after suppressing, as you increase the suppression, you will have better or larger reaction times for you to take a counteraction on. You have different sensors here. This is a multi-sensor, electro-optical multi-sensor, where you have infrared cameras, mono and stereo cameras, as well as laser ranging finders. And you have 3 different makes here: Ultra, Chess Dynamics, and Thales makes here, just to show you. Then another one, very important one, is electromagnetic signatures. You have high frequency electromagnetic issues above your hull and low frequency below your hull. And the magnetic signatures, there could be multiple reasons. When your ship moves, being a ferromagnetic material, while cutting the Earth's magnetic field, you will be causing disturbances which can be tracked using magnetic anomaly detectors. If your shaft is not properly grounded, the static current buildup can leak into the underwater radiated noise. Can be it can have extremely low frequency issues there, etc. So there are multiple ways by which you can reduce it. You can have a proper cable and wiring design. You can use a proper antenna and equipment sighting methods, active cathodic protection and filtering. Actually, your ICCP system can be, if not properly designed, can be giving out your location. Then proper material choices. There are 2 methods which may not be very familiar to the commercial designers, are degaussing and deperming. Degaussing is about using cables run through the ship's hull to send current so that you create an opposite magnetic field and cancel out the disturbance. Deperming is something you try to cancel out permanent or induced magnetic fields by some special mechanisms or special ranges. Antenna, the high frequency part, you'll have to see how the antennas are located such that they do not interfere with each other, they are compatible with each other, and you have to look at the surface current, they are not damaging each other's range and other properties. You can see the current distribution as well as the far field gain here. You have to look at the gain. And this is a radiation hazard analysis which shows approximately whether your crew it's safe to work or not when certain antennas are working. It's important. Just to show you the magnetic anomaly detectors which I mentioned before, that one is a Lockheed P3CN Orion aircraft, and the tail, the projection what you see there is a magnetic anomaly detector kept there specifically far away from its ferromagnetic materials, and on the bottom is a seeking naval helicopter where you see that that red, yellow, that's a Dunking type magnetic anomaly detector which can be lowered and towed through water to detect magnetic anomalies of ships and submarines. Crew comfort and habitability, not a signature per se, but very important because crew attention and is very important in sensing your enemy when you are in a very critical situation. So you have to limit your noises within, your noise, airborne noise as well as vibrations within limits. And it's also important, some sensors can malfunction if the limits are exceeded. Now on the left you see is a spectral energy approach airborne noise analysis where airborne, structure-borne and secondary structure-borne noise components are added logarithmically and checked against the limits. And on the right what you see is a frequency response analysis of the hull structure, and what you see here is the limits are not exceeded within those green and blue bands which are the eco and speed, the full speed modes. Vulnerability, what you see on the right is a mine damage by an Iraqi mine on USS Tripoli during the Operation Desert Storm in the Gulf War, and this vessel is sitting in dry dock in Bahrain. So this is also a slide to remember when I talk about recoverability, because this vessel was able to recover its battle damage during the operation and continue its operation, complete the operation. It's a minesweeper. So if you look at an overall vulnerability analysis, shielding, disposition and redundancy of equipment, weapons and sensors, shock grading, residual strength, damage ability, etc. Just to show you which are the major weapons that you must be worried if you are a naval ship: an anti-ship missile, multi-influence mine, which can activate itself using acoustic, magnetic, pressure, inertial, UEP, underwater electric potential, photonic signatures, and a torpedo from this thing. And you should also know about different weapons, their parameters, like your what is the head type, fragmentation, warhead mass, speed, etc. So your enemy, for example, I wouldn't say enemy, but YJ-91 anti-ship missile from China and a Turkish torpedo, heavyweight. And there are multiple tools which are used by navies around the world to do these kind of vulnerability analysis. I've just put them here. And on the right, what you see is the situation in a survivability or a vulnerability analysis, where you have a weapon strike, you have a primary damage because of the weapon, there's a secondary damage with progressive flooding or progressive fire, and then you start the recoverability phase where you start the damage control, system recovery, and then system operation at a degraded phase. Vulnerability analysis for our vessel was done using a tool called Surma, and this takes care of loss of equipment, loss of personnel, loss of stability, and also analyzes the overall mission capability in an operational readiness level from 1 to 4. And you can also look at customize your weapons and ASMs, mines, shells, and your different warheads and different kinds of explosives like TNT, combi, etc. It's a very important one which gives a lot of advanced knowledge to the operators, to the designers, etc. And part of it is an underwater explosion analysis. So we validated this against this tool which I explained before. And you have to capture the shock wave and the bubble physics, or basically the bubble from an explosion which will be pulsating up and down and which will cause ripping of your hull structure. So what you see here is a small video of that explicit dynamic analysis of an underwater explosion, and how that is captured, how it will, and the one on the left is a slightly zoomed in view, and you like to define the material appropriately. The material theory has to be appropriately defined so that you understand how the failure happens. Then next is shock transmissibility, where you will, once the shock happens, how it is transmitted into the structure or to the equipment. You'll have to look at how it is transmitted through the mounts. You'll have to look at your stress and deflection plots. So the important thing is how to define the mounts, what is the material, for example, hyperelastic or viscoelastic kind of materials, not like steel. What you see here is an acceleration plot during a shock event. Then next is, once the transmissibility is done, next is resistance of shock by, for example, foundations. Here I have shown a foundation without a mount, rigidly mounted, and you see how shock response, velocity response is shown here against shock velocity input pulse. This is again another similar case, but what is shown is a normal stress time history plot. Weapon integration, another very important thing. We'll have to look at different types of recoil forces, shock loading, missile blast, vibration, fatigue, etc. And then the firing accuracy checks could be on the right. What you see is the vessel motion power spectral density curves against the limits, which is basically looks at the vessel motions. Then external vibration and the dynamic amplification factor due to that external vibration, how vibration is affecting. And then last one on the left is weapon firing dynamic stiffness or dynamic rotation. So that your it's considered. Sensor integration is similar. You will have to also look at the electromagnetic interference.
As Vivek mentioned earlier, recoverability is the ability of the platform to restore its capabilities after sustaining a damage. There are multidisciplinary aspects in this, along with a lot of human intervention and decision making. The vulnerability analysis Vivek talked about earlier provides a lot of inputs towards this and optimizing the vessel towards recoverability point of view. Another important aspect is to have a plan of action on how to control the damage, and there are already specific systems like battle damage control systems shown here, already employed by navies around the world. Another important aspect is to have designated parties with sufficient training, designated teams with sufficient training to undertake the damage control. There are several techniques and tools employed by these parties to control the damage. The aim is to restore the vessel at the earliest, reassess the situation, and complete the mission if the degradability is within the acceptable limits. Next.
Thank you. So we have reached the concluding remarks. So we discussed today about the survivability, the concept of survivability in a naval ship. We discussed about the advanced design and building methods which are employed, and it's a proud thing to say that SEDS and CSL together had a lot of things indigenized in this process starting from 2014. We worked on this project. 2018 we won the contract, and from that point we've indigenized a lot of these advanced analytics which otherwise we were giving to foreign consultants. These are the references. And thank you. Jai Hind. I would like to end with a quote from Dr. APJ Abdul Kalam. A small aim is a crime. Have a great aim. Thank you.
Thank you.